that. So the cross sections are equilateral triangles and a circle. Hand it to me. Oh, you did not pick the right pile. Thank you. All right, so then draw your equilateral triangle. This is f minus g, which means that we have 2 square root of 4 minus x squared on each side. So equilateral triangles means that all of the sides are congruent and all of the angles are congruent. And I know some of you are taking your SATs soon. How much degrees is there in a triangle? 180. So if all angles are equal, what are we going to do with 180? Divide by 3. So we get all angles being 60. All right, so we're going to treat this like it's the base of the triangle. Area of triangle formula, 1/2 base times height. Now let's draw the triangle like a get the height situation. Now some of us, I do know, can kind of intuitively get this, or some of us, whoa, too far, can memorize the stuff that's on this table. I personally have the memory of a goldfish. You also seem to have the memory of a goldfish, seeing as we still don't know our integrals and derivatives of trig functions. So I'm feeling like you might not have the capacity to learn something new. So I'm explaining it in a way that hopefully is using the unit circle, which is something you do already know. Ideally, theoretically, is something you know. So looking at these sides, the base here, that's one more thing we should add. The height must be perpendicular to the base. So the height must be perpendicular to the base. Are any of these other sides perpendicular to the thing I said was the base? No, so then we have to make the height happen by bisecting the angle and the side. Now let's draw one of these triangles outside of the shape. Pretend that was actually a right triangle. I did not do that a very good job. Okay, we now know the hypotenuse is still that part of the equilateral triangle. We could deal with halving the height or the base, but I don't care about that. Height, I think that's more likely to confuse you. This is our height. In a 30, 60, 90, or on the unit circle, this angle is 30. It's kind of like the same thing as pi over 6. Anything on the unit circle, the radius or the hypotenuse is how much? 1. That is what is so useful about the unit circle is the radius being 1 means you can scale it up or scale it down for whatever you need to use it for. So if we're talking about the x change being the height, the change horizontally being the height, in a pi over 6, what is the x value? What's the cosine at pi over 6? Root 3 over 2. This is root 3 over 2. It is being multiplied by the hypotenuse. Oops, I meant to put 1. So to get that height, you're always going to multiply the hypotenuse by root 3 over 2. So our height here is root 3 over 2 times the hypotenuse. You don't need to do all of this if you do remember that relationship, but Hopefully, if not, you can like try to go back to your unit circle skills and like logic your way through it. So that's our height. We're at 3 over 2. We have 1/2. Our base was 2 root 4 minus x squared. And our height was square root of 3 over 2 times 2 square root of 4 minus x squared. Let's simplify. We're left with square root of 3 times the 4 minus x squared is multiplying another 4 minus x squared. So the square root of 4 minus x squared times square root of 4 minus x squared. So the square roots cancel out. This is our area of every single equilateral triangle. Now remember, in this shape, we are doing a little equilateral triangle here, then a slightly bigger one, then a bigger one, then a bigger one. You're accumulating all of these equilateral triangles as you get over here. And you're going to have the same amount and the same size equilateral triangles. Find the areas over here. So what we are integrating from -2 to 2, but what else could we do instead? So if we're integrating, look at the symmetry. If the amount of area and amount of triangles is equal on the left of the y-axis as it is to the right of the y-axis, what could we do instead? Tate. Yeah, 0 to 2 and double it. So our volume, we're accumulating the areas from -2 to 2, but because of y-axis symmetry, we can change that to 0 and double it. This only works if the base shape is like the circle or whatever function is symmetric about the y-axis. Some of you on the quiz today had a shape that looked like this, if you graphed it correctly. That had x-axis symmetry. So you could have doubled from 0 to 2 the right minus left because it had x-axis symmetry and it was a dy problem. So it's like, remember, whenever we're dy, we're kind of switching all the rules around, like inversing them back and forth. Ooh, so cutesy. All right, and then area square root 3, 4 minus x squared dx. And boop, 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 equals 32 square root of 3 over 3. Questions on the equilateral triangle? Colin.
How do we get the initial formula for side would be 2 root 4 minus x squared?
The base one?
Yeah, base.
So like, and this, I was treating this whole length as the base.
Yeah.
And then the height, I had to like cut it in half.
Yeah, but how do we get the base? Just how do we figure that out?
Oh, because it was a circle.
Okay.
So like all the bases were along that circle doing top minus bottom. So they were doing square root of 4 minus x squared minus negative square root of 4 minus x squared. Like the
So
blue.
why do we have to do top minus bottom to the base then?
Right, so top was square root of 4 minus x squared.
I know, but how did we figure that part out? Like, why did we have to do a top minus bottom?
Because it's a circle, so we had to solve for y equals,
Oh,
right? So like the circle becomes y equals plus and minus square root.
therefore, when it's a plus and minus, you have to do both.
Yeah, because that's like the top is that where it's blue, and the bottom part of the curve is the yellow. That's like how, like if you just did square root of 4 minus x squared, you would have been having like half the size of the triangles or whatever cross-section shape. All right, do we want to go over D again? Or do we feel okay on D? Yeah. Here we can do it with, it is the same thing as root 2 over 2. And you could just multiply it by root 2 over 2. I just felt like the algebra would have been easier, but it really didn't matter. It's just like technically what you are doing is you are dividing the hypotenuse by the square root of 2, but you also could just think of it as multiplying the hypotenuse by root 2 over 2. That works as well. So like your algebra over here, if you had done the equilateral triangle with root 2 over 2, you would have 1/2 square root of 2 over 2 times 2 root 4 minus x squared squared. That second parentheses is wrong. Because like this, the base and the height were the same as each other. And it still would have like simplified to be the same thing because you would have had these could simplify and you would have 2 times 4 minus x squared. And then those simplify. And now we're integrating 0, 2, which is what we had on the left as well. It's just like the 1 over root 2 is not rationalized, and then root 2 over 2 is rationalized. But either one should work. So you could either know, like, probably you're more familiar with knowing square root 2 over 2 for 45, 45, 90, so we just multiply the hypotenuse, or the hypotenuse by root 2 over 2. All right, try to do E as in everyone will get this one right. So we're saying the cross sections are perpendicular to the x-axis, and it's an isosceles right triangle with a leg on the circle. So Colin, this is the same, the leg is still top minus bottom, so it's still 2 square root of 4 minus x squared. So that's my leg. It's kind of looking to me the way I drew it like it's the height. So what would my base be? That same exact thing, right? Because it's an isosceles right triangle. So if you get the leg on the shape, such an easier situation than the hypotenuse on the shape. Hypotenuse on the shape is like a nightmare. Leg on shape, much better. Okay, so on this one, what is something you're not going to do because you would never make this mistake, but someone would maybe do? Cancel the 2's out, the half and the 2. Why is that not correct? Yes, we have to follow our order of operations. There's a square. Once you square it, now you can reduce and say the area is 2 times 4 minus x squared. And then our volume, 0 to 2, 2, 4 minus x squared dx. So the reason we like to do the 0 to 2 is because then the plug-in steps are a lot easier. I'm not plugging in -2 into both of those. I guess we could stop here, but I can't help myself. It's like a compulsion. I have to keep going. Okay, so the next page is for our friends who are great at memorizing. That is not me. And then let's do 1.5. So 1.5b, as in the best. I like this section. Okay, 1.5, varying weights. Let's zoom all the way up. So today, what we're going to do is have like a chain or a rope hanging off of something. We're trying to figure out the work required to pull whatever object is hanging from the rope up. So if you think about the force acting on, if I have something hanging off a rope, it's really a lot of force, like really far down, and then gets like, different forces as the amount of chain, because this has weight too. The chain is a weight, or a rope has some weight to it. So there's like more force, there's more pounds hanging down, and then when I pull it up, there's less rope, so there's less pounds and less force. Yes. Okay, so today I'm going to try to explain in 2 ways how to do the same problem, because I visualize it one way, but that does not mean that that's the only way to visualize it, and some of you might see it in a different way, and I will try to explain it both ways. I will let you know the origin at the bottom is the way that I see these. So this is origin at the bottom. So saying like down at the ocean floor, I said bottom. The height is 0 feet. And at the top, we have now moved, let's maybe read the problem first. Okay. A ship is anchored 100 feet of water. So it just so happens that where they put the anchor down, there was the ship, and then to get the anchor to the floor was 100 feet. The ocean has very different depths at different places. So like every problem is not going to be in 100 feet of water. The anchor weighs 4,500 pounds. So the anchor is 4,500 pounds, and the chain weighs 25 pounds per foot. So the anchor, no matter the depth that we have, this anchor will always be 4,500 pounds. So it always has a force of 4,500 pounds. The chain, though, as we pull the chain onto the boat, we'll have less and less chain hanging down. And what the amount of chain hanging down is what we're actually trying to measure. And then we're trying to figure out the work required to move the anchor onto the boat. Okay, so if we have the origin at the bottom, I don't like the arrow going this way. To move up from 0 towards 100 feet above, I'm moving positively in the y direction. So I've moved up y. Then if we're starting, this is at 100 feet from 0. This is actually the amount of chain we're trying to figure out. Once I've moved this anchor up y amount, I still have this much chain hanging down from the boat. So that is the part of the chain that really matters. How much chain is that? How much feet of chain? If I move y amount, and that was at 100 feet, how much is left? 100 minus y. And that, I think, is confuzzling for some people. So let's try to explain what that means in something that maybe will make more sense. So this is 0, this is 6. And I say I move this direction 2. From 6, how far away is it? 4. It is 6 minus 2 is 4 away. So if I moved to the right some x amount, but I really want to figure out this difference from x to 6, what would it be? 6 minus x. So it's the same idea, just kind of like switch the orientation around. I've moved y amount, but I really want to figure out the displacement from 100 feet to that y location. So it's 100 minus y. This is my personal preference. So I prefer this. So if you look at my examples and my solutions, I'm mostly going to be using this way of doing it. But today I'm going to try to explain for this example how to do it, if you think of the origin being at the top. So if we think of the origin at top, I think some people this will make sense for you, because if 0, 0 is at the top, that's like water level, and we go down, we're going down y. So y going below sea level is going negative. And then coming up from the bottom is at negative 100 feet. And I have to do y plus 100. So like go that distance, but like opposite direction. I don't really like doing it this way because it always will deal with negatives. And to me, I feel really nervous when negatives get involved. I just a baby when it comes to negative, and I'm going to like mess that up for sure. And you're going to see in 2.3, when we start doing trig sub, I always set up triangles trying to avoid negative derivatives because, again, I'm going to screw up the negatives. So I don't love the way on the right, but I do know that some of you will be like, that makes sense to me. And so do it that way. I don't care what way you do it. I will understand. I do have big brain. I just personally avoid the negatives, but you do you, boo. Okay, so looking at A. When the anchor is at the bottom, we're neglecting buoyancy because that's a whole other force that you'll get into if you become an engineer. But how much work is required to bring the anchor aboard? Now remember, no matter what the depth is, how much does the anchor weigh? 4,500 pounds. So the anchor is constant of 4,500 pounds. So if we have a constant force, we do not need to integrate. We can just use your good old physics 1 definition of work as doing force times distance. So our force, 4,500 pounds. What was our distance to go from the bottom all the way up? 100 feet. Someone in second period asked if we need to have units. Yes. And I do think it would behoove you to have the units when you're writing it in the middle of the problem. The reason for that is if you are dealing with force, today we're going to have to figure out getting the force equation is going to be the most complicated part. If you're dealing with force, it needs to be in pounds. If you're dealing with work, it needs to be the force times the distance, so it should be pounds times feet. And you can know that you have set it up right when you have the correct units. We're going to have things that are like feet per second or pounds per foot, and you have to like convert between the different units and end up all in pounds. All right, so now looking at B. When the anchor is 45 feet from the bottom, how much work? And again, it's just hanging 45 feet from the bottom. So 45, what the heck, 75. 75 feet from the bottom. So let's look at our beautiful chart over here. 75 feet from the bottom. So the distance from maybe I'll actually draw it. From the bottom, 75 feet. How much chain is actually left hanging down? 25 feet of chain. 100 minus 75. Okay, so our fort is just hanging there, still just the anchor. Our work would be what times what? What do we think? Tate, what do you think? So what are we doing?
Force is 4,500. What is the chain distance?
No, just the anchor.
Just 4,500, and then 4,500 times 25.
Yes. Beep boop beep boop boop. Very official calculator noise. Okay, part C, you kind of need more room. I should probably edit that for next year. Maybe I'll remember to do that today, but probably not. So part C, try to write small. We are going to do both scenarios with the origin at the bottom and the origin at the top. I just want to be able to like show for our friends who need to see it a different way. The force between the bottom of the ocean and water level, the force varies linearly with the length of the chain. We kind of could tell that the length of the chain was going to have a varying force because its weight was 25 pounds per foot that it moved. So it's like how much the chain weighs depends on how deep into the water it is. So using both scenarios, that means like origin at the bottom, origin at the top. We're going to figure out the force if we're just having the chain and the anchor halfway from ocean level, and then the chain and the anchor 25 feet from ocean level. So over here, we're going to have the origin at the bottom. And over here, we're going to have the origin at the top. Regardless of which way you think of it, you need to know that if you have multiple forces acting in a system, that we have to do the sum of the forces. You have to kind of like it would help, I think, to identify your forces. So we have the force of the anchor, or the weight of the anchor, and we have the chain. And if it's a force, the units we're in are in pounds. Is the weight or the force of the anchor changing or constant? Constant. So this is constant. A little C for constant. Is the force of the chain changing or constant? Changing. Oh, I should say varying. Varying, because they would both be C's if I said changing versus constant. Okay, now we're going to split down the middle. Ooh.
Good afternoon, everyone. Pardon the interruption. This one's right hot off the wire. Boys and girls practice for golf today is canceled. Again, boys and girls practice for golf is canceled, and we are still under a weather watch. Thank you.
Too bad you don't have your phones to tell your parents that's canceled, you know what I'm saying? Okay, so we got 0 at the bottom, the origin's at the bottom, and then 100 feet at the top. And remember, we're moving, the chain has moved up Y amount because it's going positively up, but we don't actually care about that distance. This is where the chain actually is green. So what is that distance? 100 minus Y feet. And how much per foot was happening again? I don't remember. 25 pounds per foot. So the chain, we have 25 pounds per foot times our 100 minus Y feet. Do you see how the units are going to cancel each other out? And now we are just left in terms of pounds, which is what we want. We need the force equation to only be in terms of pounds. That's why I like to include the units when I write these steps, because I know that I'm in the right units. I have the force ready to go. All right, so let's write our force equation. We have the force of the anchor, constant 4,500 pounds, and the force of the chain, 25 times 100 minus Y pounds. Are there questions about how we got to that? That'd be the key. Okay, so now let's try to do halfway. If I had moved the chain halfway up or down, how many feet have I moved it? 50. I'm plugging in. And I get beep, boop, beep, boop, boop. 5, 7, 50 pounds. 57, 50 pounds. Okay, the next one. When the anchor is 25 feet from ocean level. So it's like, it's moved up 25 feet. So 100 minus 25 is 75. Beep, boop, beep, boop, beep. Okay. On the origin at the top side. Origin's at the top, so we have y equals 0 feet. Now we're moving down y amount. That's really the only part we actually care about, but whatever. And if we're going down negative y, because you're saying now when I go below the surface of the water, the height is negative because it's like below water level or sea level or whatever it's called. What would the y be at the bottom then? Negative 100 feet. So our force equation, if you understood what I did on the left side, you can shut your ears off and just think about, I don't know, the lighting in this room. So we still have the force of this anchor, but now the force of the chain is going to be 25 pounds per foot times negative y feet, which leaves us in negative 25 pounds as that unit. So in this case, if I'm going to the halfway point, I'm going to negative 50. I'm going down 50. Beep, boop, beep, beep, beep. Same number. And then if I am going, when the anchor is 25 from ocean level, I think that really means like the top of the ocean level. I think the wording there was a little bit wonky. Going down 25 feet. What is it? 1? Okay, so that's just the force at a specific location. Now we're going to do the work for both scenarios to lift the anchor all the way to the top of the boat. I decided this year versus in previous years to show you both ways because inevitably someone comes in and it's like, could I do it this way? And I'm like, yes. So, you do you, boo. So doing the work, what does the work, now we have a variable in our forcing equation. So what does work equal no matter what scenario we're doing? No, it's not constant. Integral of force. Okay, so now we have, on the origin at the bottom part, our work, we're integrating that force equation. Sure, you could totally simplify it. I am not going to. So I'm going from the bottom of the ocean to the boat at 100 feet away. What is my lower bound? What's my upper bound? 100. If this was a no calculator allowed quiz for whatever reason, my directions would probably be set up but don't evaluate the expression for the work to lift it, blah, 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 feet or whatever. But, beep, boop, beep, boop, boop, 575,000 foot-pounds. Okay, so on a quiz, if this was calculator allowed, please have your integral written on your paper. Don't just have the answer. If your answer, maybe you had a fat finger moment and you left off the second zero of 4,500, and your answer's totally wrong, and you have no work, I have no idea what you did. So I can give you 0 points for that. But if you have the integral, and like maybe this is like off and there's a 3 or something, I can be like -1 because you typed something, you lost your mind. I don't know what happened when you were typing in the calculator, but you done goofed. But if the integral is right, you get most of the points. I'm like, yay. That was the point, was doing the setting up of the calculus. Because you don't know how to use your calculator, will not earn you full credit, but it will earn you most of the credit as long as your calculus is set up right. All right, now the work the other way. looking at what is our lower at the sea floor, what is the bottom? Negative 100, and then we're going to 0. I just don't like it. I don't like having negative boundaries if I can avoid it, but it's okay. If you like it, I like that for you. Okay, here is the real question, the real deal. Example 2. So example 1 is just like really like step by step, each like kind of way we could hopefully think about doing this problem. Example 2 is way more likely the type of thing I'm going to put on a quiz or a test without the leg. Now think about the force. Now do the work. Just like you got to do the whole thing. So we have a leaky 5-pound bucket is raised 20 feet. The rope weighs 0.08 pounds per foot. The bucket starts with 16 pounds of water and is empty when it reaches the top. How much work is done to lift it to the top? So you didn't know, I'm imagining this being like a well, right? And you like stuck this like old school bucket that just has like flat boards of wood stuck together, and there's like all these little gaps in between. And you stuck it down the well, and now you're lifting it up, and you're like, son of a biscuit. Now it's at the top and I have no water, and I did all this work to get there. Just so happens that's empty at the top. Every problem's not going to be empty at the top. We'll do a classwork problem just to show you that it's not going to always be empty, because otherwise what the F would be the point. Okay, so the sum of the forces, we have the bucket. No matter how deep the bucket is, it's always 5 pounds. Then we have the rope. And the water is changing, right? We start with 16 pounds and then we end with 0 pounds. So the weight of the water is not included in the weight of our bucket. I'm going to draw this with the origin at the bottom. But first, before I draw it, let's think about what's happening. The weight of the bucket, is that constant or varying? It's constant. It's always going to be 5 pounds. The weight of the rope, constant or varying? Varying, because as you pull more rope up, less rope is hanging off of, the weight is just how much is left hanging off of like the pulley system or whatever you're doing. How about the water? Also varying. It has to be varying, and it has to be varying linearly because the water is dripping out at a constant rate. We're assuming that the water is being lost at a constant rate. And it's not quadratic because like you're not gonna like lose water and gain water. So it has to be linear. We're just like constantly losing a certain amount. We'll figure out how much it is. All right, I'm gonna draw near the bottom of the page. Super beautiful picture here. This is my bucket. So I'm saying at the bottom is 0 feet. How much feet is at the top? 20. I thought you said 120. Okay, and then as we move the bucket up, we're losing this Y amount. We don't have Y because there's still this much rope hanging down. So this is the amount where the force is actually happening. This is the part we care about. So how much feet of rope is just dangling down at any Y moment? 20 minus Y. And then it said the rope weighs 0.08 pounds per foot. And we have dangling off at any moment of time 20 minus Y feet. Feet cancel. That is the force at any Y height of the rope. I'm going to put it up here. What is our variable right now? Y. So we're going to keep it as y in the next part of this. Okay, so our variable is y. At the bottom, how much water, how much water is in the bucket at the bottom? £16. How much was at the top? £0. And what variable do we want to use to represent the water? Do we want W or H? Like W for water or H for H2O? Okay. So our water is W. As we are lifting this bucket up, we are losing water with respect to the height of the bucket, or the Y. So our water depends our water weight depends on the depth, or the Y. The Y is our independent variable. We already said that there's a linear relationship between the depth and the weight of the water. So we can write the equation of a line, because there is a linear relationship. So this is a linear relationship. So linear relationship. Let's write the equation with line. Yes, you could do y equals mx plus b. No me gusta y equals mx plus b. I like point slope. Some of you also will intuitively just understand what is happening here and probably can skip this step. For the rest of us, I'm going to show you the step-by-step how to get it if you're not like intuitively getting what's going on here. So we have a linear relationship. We know point slope usually as y minus y1 equals m times x minus x1. Whereas like dependent minus dependent equals the change in the dependent over the change in the independent times the independence. So instead, we had to figure out our relationship. Ordered pairs go independent, comma, dependent. So here our variable that is independent is what? Ben?
Height.
The height. So if you want to use h, then you have to change everything to h. You have to change the rest of like the top equation to h. I'm going to do w. I mean y. And then our dependent is the weight of the water, so w. This is where people's brain guts are going to like splatter on the roof. If the fact that my independent variable is y bothers you, change it to height. But that means that you also have to change this to height too. So just change it everywhere. Now you're going dh. It literally doesn't matter what the variable is. You just have to understand which one's independent and which one's dependent. So we are going to have w minus w1 equals m times y minus y1. At the bottom, what would our ordered pair be at the bottom? 0, 16. At the top, ordered pair at the top would be 20, 0. Okay, now finding my slope. Slope is the change in the dependent over the change in the independent. Doesn't matter which point you decide to use, just roll with it. So I got 16 minus 0 over 0 minus 20. There's not a reason that I chose to do the bottom as y2. It just doesn't matter. And we got, let's match our highlighter here. Just make sure that the ordered pairs are stacked on top of each other. And this would simplify to be 16 over negative 20 or negative 4/5. So that is my slope. So plugging in W, negative 4/5. It does not matter which ordered pair you use to plug into point slope. One of them is the y-intercept, so one of them might be easier to deal with. 16 is the y-intercept, so now I won't have to distribute the negative 4/5 to a number, but you could also have done w minus 0 equals negative 4/5 y minus 20. That will work as well. Okay, and I think also I was saying stuff about the units, and I kind of forgot to write them, so let me just write them real quick. So our dependent variable was water, and water was in pounds. Our independent variable was the y, the depth, so it was in pounds per feet. Our slope is pounds per feet. So in here you have pounds per feet. Whoops, that's not a 16, that's a B. All right, pounds per feet. And then the independent variable, the y, is also in feet. So we are left in pounds. The dependent variable 16 was in pounds. So when you solve this, negative 4/5 y plus 16 is in pounds. So it is a force. Add that into the equation. Way up here. And now we are that's our force equation. Obviously this force is varying. What would work be? The integral of that force. So if you have iPad magic, you just could copy and paste that on down. If you don't, sorry for your loss. Don't care. And then what are the boundaries going to be? The height from the bottom to the top. Where in terms of dy, it needs to be those y boundaries. I'm trying to figure out how much work to go from the bottom, 0 feet, to the top, 20 feet. Because remember, work is force times displacement. So this force equation is then going to be like multiply by a y in each term, and then you're going to put in the displacement between the two of them. So it still will give you force times displacement. And beep, boop, beep, boop, boop. Yay. Yeah. Because I'm done. Because I was thinking of the last problem. Okay, we're doing number 4 on the classwork. Number 4 is slightly different and will stretch your brains a little bit. As if they were an RV stretch. If they are not calculator, then I would set up the expression. I probably wouldn't even say the integral. Which is really what I look at anyways when I'm grading things out the calculator. I like look to see how it goes. Just number 4. There's so much time. Or slow. Yeah. I'll just scooch it all back together. Scooch it on in. We're working together. And I'm also going to pass out your homework too. I know you're so You may use your calculator, but make sure it's set up.
schedule's on there. Can we do tomorrow?
What do you think?
Probably.
When does Barb usually do it?
I mean, it's usually do Sunday, but you never know.
You never do know. You never know.
Safer to ask than to not know.
Sure, that's true.
Okay, so for the first one, you can wait for the offset and wait on water.
Holland, Sunday.
Great, thank you, appreciate it.
I mean, what else?
You could do some of them and ask me questions tomorrow.
Yes, of course. But it's when do they all need to be finished? Yes, I'm busy